Welcome to the next video in circuit protection. In this video and the next one we're going to cover issues with the selection of protective devices, and there are 5 issues that we need to cover for this course in particular, and they are earth leakage, overload, mechanical overload, loss of phase, and short circuit. So we have problem number 1, an underrated RCD. Somehow a 10 milliamp RCD has been put into a domestic situation, and there's more than 10 milliamps earth leakage in the circuits that are protecting, and it's tripping out. That can be a real problem. Just an aside here quickly, you see the 40 amps on this. That is the RCD current rating. It's the rating of the contacts of the RCD of what current it can safely break. This is one rating that you need to take into account when you're purchasing RCDs, that they're big enough to cover the circuit that they are protecting. The sensitivity or the tripping current of the RCD is the one that we're actually looking at here. In this case it's 10 milliamps, and that's how much of an imbalance this RCD will act on to cause it to trip. And 10 milliamps is not very much current at all. In actual fact, we should have 30 milliamp RCDs in domestic situations. That's because you can get just a few leaky domestic appliances like washing machines, dryers, jugs, all adding up together to be more than 10 milliamps fairly easily. The trade-off is we're going to get a 30 milliamp shock from an RCD before it'll trip, and in a domestic situation hopefully we're all good and healthy, and a bit of a jolt for 30 milliamps might make our arm twitch, but it still won't hurt us and it'll still be over and done with in less than a heartbeat. So problem 2 is an overrated RCD. Now this is kind of obviously the opposite of the one we've just had. We've got an earth leakage fault, and we've put a 30 milliamp RCD in a hospital or kindergarten or school. Now the problem we have here is that we're going to get a 30 milliamp shock, and if we're a young child at kindergarten or at school, or if we're an elderly person, or if we're sick and we're not doing well in the first place, this 30 milliamp is going to cause muscle contractions, and it might actually hurt us. So in schools and hospitals we're going to choose a 10 milliamp circuit breaker. This one is a 30 milliamp, and it's not right for the situation. Problem 3, incorrect utilization category. So we've got a GM fuse on a lighting circuit. Can you remember what GM stands for? It's going to interrupt short circuits and overloads, but it's also motor rated. Now motor rated means there's going to be quite a delay before it does anything. If we put a GM fuse on a lighting circuit and we have an overload, then it's not going to work very well, is it? So just a reminder, the utilization category is a 2-letter code for fuses. The first small letter is the range of braking, and the second is a capital letter, and it's the type of protection this fuse offers. And as we said, this is a motor rated fuse, so we don't want to use a motor rated fuse on lighting. We could have a fault that it doesn't stop, and we can have a fire or someone be electrocuted. So problem 4, a wrong fusing or tripping factor. You remember that tripping factor? And let's say we have a loss of one phase in a motor. It's going to cause higher current in the other phases, 2 phases of a 3-phase motor, and it's going to need to trip out because it's an overload situation. Let's say, for instance, I don't know how it happened, we managed to get this motor being fed from rewirable fuses, which are not very close in their protection. They're actually coarse protection, and they're not going to trip in time, or in this case fuse in time, and we're going to burn the motor out. Not a good plan. We need to have protection that's suitable for the situation. So what about if we use the wrong class of fuse or circuit breaker? Now we've talked. This is similar in a way to the wrong utilization category, and we might have a mechanical overload as suggested here. Mechanical overload is where for some reason a motor is jammed and can't turn, and the windings start to overheat and the current overloads in the windings. If we've got the wrong class of fuse, we can have the wrong class either way. We can have too closer protection like the P, and that would it would trip out or fuse on startup of the motor, or we could have an R where this overload goes on for too long and burns the motor out before the fuse burns out. So relating this to circuit breakers, there are different curves of circuit breakers which are like classes, and curve B circuit breaker, it takes 3 to 5 times the rated current of the circuit breaker to be flowing through that circuit breaker before it trips instantly on the magnetic latch. If you remember, we've got the thermal bimetal, which is a slow protection which allows for overcurrents of short duration, but then we've got, for short circuits, we've got the magnetic latch mechanism and release mechanism which instantly operates. So in a curve B, it takes 3 to 5 times the rated current of the circuit breaker. So if it's a 10 amp circuit breaker and you have 30 to 50 amps flowing through it, it's going to trip. Then we've got C curve, which you'll see in most domestic situations, and it's slightly less sensitive, and it takes 5 to 10 times the rated current for it to trip out fairly instantly. Then we've got D curves. It's 10 to 14 times the rated current. Imagine that. Wow, and this is a 32 amp. I'd have to get my calculator out. It's 320 plus amps to make this trip instantly, and we'd use that for, as it says here, high surge circuits, welders, transformers, motors. It's like a motor rated. And there's even one more. It's the MA curve. It takes 12 times the rated current, and it's protection specifically for motor starters. So when you're choosing protection devices, you need to, in particular if it's a circuit breaker, you need to bear in mind the type of curve you're purchasing. If you're doing domestic work, generally you're just going to the wholesaler and grabbing a C. But if you know that you have to protect it in a different way, you'd go and ask for a different type of circuit breaker. Right, insufficient rupturing capacity, and we've got a short circuit. Here we go, look at this. Do you reckon this fuse, this rewirable fuse, is doing a good job? It's going to rupture this current, but in the meantime it's created a dangerous situation. It's really overloaded at this current. So the rupturing capacity or breaking capacity of a protection device is the maximum, remember, the maximum current that can be safely interrupted by a protective device. And we need a protective device that's going to have a rupturing capacity that's higher than the prospective short circuit current that we're going to get in a fault, higher than the highest current that we're expecting in a fault situation. Now, HRC fuses, high rupturing capacities fuses, they are really quite amazing. 80 Ka for this one here. I chose this photo because it's actually failed. This fuse here is actually in a melted fuse holder, and the fuse itself is melted. That's because it's had a loose connection to it. This fuse, I find it ironic that this fuse is able to stop 80,000 amps, yet there's been a bit of arcing going on here in the holder, and it's ruined the fuse. So just a point there, you know, it doesn't matter how good the circuit protection is, if you've done a bad connection, you can still cause problems. But anyway, back to insufficient rupturing capacity. This one does 80,000 amps. What do you reckon this one does? Is it written on there? Yes, it is. You can see a little house and a fence. That's cute. It means that it's rated for domestic, and it's rated at 6,000 amps. That's the rupturing capacity or interrupting ability of this circuit breaker. So that brings us to the end of this video on circuit protection.